So, the rise of reactive microservices. Who ever heard about reactive systems? Cool. That's the right conference, I think, for this topic. Who knows the reactive manifest? Good, because I don't have it on the slides. Yeah. Cool. So I will talk about the journey from, or our journey, or I think journey from most of us, from classical microservices to more and more reactive or stream-based microservices. So as Manuel mentioned, I'm a coding architect at Square. So I even had this title before. Patrick Kuh in the morning said that software architect seems to be a bad term because I think it describes my work very well because that's basically what I do. And actually, yeah, if you want to reach out also, you find me on Twitter, you find me an email. I think that's the usual stuff. But let's come to the important part. Yeah? So this talk is called The Rise of Reactive Microservices. So it's very essential to understand what reactivity is all about, right? And reactivity is kind of a often used term these days. So we have a lot of frameworks, right, which are called React, for example, or Project Reactor in the Spring ecosystem, very strong, or reactive extensions actually living everywhere. So reactive seems to be an important pattern, important principle when it comes to engineering. And of course, there are many more. So I just looked up the other day an old project of mine. Does anybody still know Bacon.js? No? Oh, a fantastic JavaScript library for reactive programming. So there's, I mean, we could talk the whole slot about just frameworks which exist in this era and how they are different and how some of them are better, some of them are not so good. But that would be too opinionated. So let's better talk about what reactivity is in general about. So it's programming or designing upon asynchronous data streams. That's a very important message. So it's about streams. So finally we're there. So I think, as Manuel already mentioned, I like to talk a lot about Kafka usually. So I like to talk a lot about streams. So we are here, it's about streams. So the question which of course occurs, and obviously I often have the feeling that that's not even so clear what a stream is if I talk in projects or in initiatives about this concept of streaming. And the simple answer of course would be everything is a stream, right? Yeah, unfortunately it's not like this, but I also teach at university, and I always try to explain my students very simply what a stream is. And I think the best explanation I got so far is describing it based on data structures, right? Because on a theoretical level, a stream is something quite natural in programming. And this slide now seems much more complex than it actually is, and I bring it very often when I talk about Kafka and other things, event-driven architectures, but it usually, does a good job. And when we talk about data structures in software engineering, we actually have two axes. We have the axis of space and we have the axis of time, right? And if you stay in singular space and say in synchronous time, then we have a data structure we are all aware of, which you usually tend to call a value, and the value has a getter and a setter. Yeah? So you see it's not that complex as it seems to look like. Yeah? And if we go from singular space to plural space, but stay in synchronous time, then we tend to have something which we tend to call a collection with an iterator and with a generator in general, right? So on the synchronous time, things are very obvious because most programming languages, most frameworks come with these data containers out of the box. They are first-class citizens nearly everywhere. Yeah, there's no programming language that doesn't have a collection, right? There's no programming language that doesn't have a value anymore these days. But when we move from synchronous time to asynchronous time, then we have something which we tend to call a promise. And the promise over the last couple of years came a first-class citizen in many programming languages. So a promise is basically, I think, driven by the ECMAScript community, but then actually in Java, C#, everywhere you have kind of the concept of promises, something which tells you that you will get a result in the future. Eh? It's kind of a bad promise, we know, because you don't always get the result. Sometimes you get an error, but in general, the idea is very simple, right? And you usually have a deferred and you have a resolver. And now, I mean, they always question where's the stream, right? And now the stream fits naturally in. The stream is in plural space and in asynchronous time, right? It's like a collection which kind of produces values over time, so not synchronously, but asynchronously. And I think that's the best explanation you can get if you need to explain somebody what a stream in essence is, because it's no magic, it's just like this. It has a subscriber and there's an emitter. And the thing is, that this is usually not part of most programming languages or frameworks out there, right? This is not treated as a first-class citizen. You need to have some reactive extensions libraries to actually get this data type into your software. And yeah, streams are just another data structure, so we clarified this. And yeah, as I mentioned, for example, reactive extension is nothing else than providing this data structure to your ecosystem, right? That's where I have it for nearly all languages. But coming back to the title of this talk, what has this all to do with reactivity, right? Well, as I mentioned, reactivity is designing or programming upon asynchronous data streams. And again, very simple example. What this actually means. Why is reactive programming built upon asynchronous data streams? Well, here's an example for you. So we have a counter variable 2 and we have a doubled variable counter multiplied by 2. So big prize question, what's the value of doubled? It's 42, yeah. It's 4, yeah, okay. So let's make the assertion and the test will run, right? That's simple. I guess everybody can follow. So let's change the code a little bit and let's update the counter to 3, right? Genius comment, by the way. Update counter. For whatever reason, we update it by 3. And now, you know, if we would make an assertion and if we would consider now doubled to be still the doubled value of counter, then we could assume it's 6, right? But actually, this is where our reactive heart breaks, because that's not the thing in our usual programming model, right? This is not what's happening. We need to reassign doubled, of course. We need to say doubled is counter multiplied by 2, and then we can make the assertion, and the assertion will work. And basically, that's the whole criticism on the reactive community and how we solve problems right now, right? Because this relation between counter and double is very implicit. It just exists in the head of us as developers, and we need to take sure that those two things are kind of bounded. And basically, much smarter people than me found this out quite a while ago. Reactive programming is an age-old concept, but kind of great article on this was from Paul Stovall. I'm not sure if you know him. He's quite popular in the reactive community. And he actually introduced a solution for this problem, and he called it the destiny operator. And the destiny operator is actually a way to make this snippet here reactive. And if we think about the destiny operator, then what it basically does, it binds doubled and counter. So how does the destiny operator look like? We have here this small, tiny hand. Can you see it? Yeah, cool. So this is the destiny operator. And what the destiny operator does, it binds counter to doubled. So whenever we change counter, in this case again to 3, then this assertion would work. That's the theoretical concept of the destiny operator. And the destiny operator itself is always implemented with streams. So if we go to a more real-world code snippet, it will probably look like this, right? We have a counter with a stream with the initial value of 2. So if we take a look at the stream, it has one value, it's 2. And then what we actually do is we project the counter stream into a new stream. So we take the counter stream, map it, multiply its values by 2, and assign it to a new stream, which is called doubled. So we do stream projection. We will come back to this later on architecture level. And then we actually have a second stream, as I mentioned, which then has a value of 4. And if you then change counter, all you need to do is you basically go there and change here a few lines of code and emit a new value, right? So you go to the counter stream, emit a new value of 3. This actually changes the stream. So we have a new value of 3 there. And actually, as we kind of just projected one stream into another one, our double stream will automatically change and our assertion will work again, right? So again, just kind of pseudocode, but in reality it looks very similar. If you ever did Angular or reactive extensions in general, then you basically have a very similar syntax, right? You have a behavior subject with an initial value of 2, right? And then basically you project this stream of counter into a new stream. So you pipe it and you basically map it. And then you have a new stream which is called doubled. And if you want to change counter, you basically do the same thing which I just did. You emit a new value to counter, and ultimately then you can assert that doubled value is 6. And this test really, I will not run it now, but this test will pass, right? So that's basically the idea. And in more modern frameworks like Svelte, for example, they come with more sophisticated concepts for this. So if you have a counter variable 2 here, you have a doubled variable which is counter multiplied by 2, and you see this tiny $ sign here in front. this is basically telling Svelte, hey, this is a reactive variable. So bind this variable to all the context it needs to be calculated. So we bind doubled to counter. And if we then just go there and say counter is 3, then in Svelte we would be sure that doubled would still be 6. And I mean, that's very close to the destiny operator originally proposed, right? And I know it's not cool that I propose Svelte here as the new kid on block. It's in JavaScript terms already age old. And if you're really interested in how languages drive this further, then Solid.js, for example, is a fantastic use case. Yeah, take a look at their reactive implementation, how they really bring this into their language and into their framework. So it's for sure one of the coolest reactive frameworks out there right now. I would say on all stacks. Yeah, cool dodge. Okay, so you are now all on the same page. Everybody's aware what reactive programming means. So it's programming and designing upon asynchronous data streams. Okay, but this talk was not about reactive programming. It was also not about software design. It was about software architecture, because microservices is a software architectural pattern or concept. So as often in software engineering, we basically can use similar concepts, for example, from software design, and also apply them on software architecture. So Greg Young will later have a talk, I think, on CQS, right? He coined this term. And that's a good example, because we had CQS also in object-oriented programming, right? Without the R. And then we moved it to an architectural level to have CQRS out of it, right? And the same we can basically do with reactivity. So if you understand reactive programming, the concepts are actually very similar, right? We can apply those concepts of reactive programming on architecture as well. That's why I'm so keen on giving you this, I know, very low level and simple introduction to what we're actually talking about. And then we hope that it still makes sense, of course, right? There's again the dodge, yeah. I spend too much time on Slack. I think 50% of my brain capacity is just thinking of Slack emojis all the time. So, let's talk about architecture, and I again made up a simple use case, but it's very close to what we usually see in reality. So what has this all to do with microservices? Well, give me a few minutes, and I will explain you. So let's assume classical microservice architecture. I know there is no classical microservice architecture, but let's come with an example which is kind of reasonable and which doesn't bloat this whole talk now, right? So we have a couple of microservices. We have a user microservice, we have account microservice, and we have a ledger microservice. And I'm working mainly in fintech and banking industry, so I know this domain best. That's why I chose it. You could apply any other domain. Doesn't really matter. And then we have a web banking application where you can trigger, for example, a new payment from myself, I guess, to Lisa. And if I perform this payment, then this web banking application would probably go to a user microservice, would say, hey, let's transfer some money. The user microservice would go to the account microservice and would say, trigger a payment. The account microservice would go to the ledger and say, create a transaction, beep-a-bo. Everything works fine, cool. We get back the green arrows, and the payment was successfully executed, right? How does this sound? This sounds like the happy path, right? That's usually never happening like this, because in distributed systems, we know everything that can go wrong will go wrong, right? So probably we do the same thing again, transfer money, trigger a payment, create a transaction, and then we have ledger. Everybody who worked in core banking systems or also in newer ledgers knows that ledgers are kind of, very special systems, and sometimes they just don't want to work as they should work, right? And then you trigger a payment, and then your payment just is stuck, right? Ledger doesn't answer, so maybe we run in a timeout, maybe we're not, but it doesn't really matter, because whenever you did a payment online, right, and you're stuck in front of a loading screen, it's just a fucked up user experience, right? It just doesn't make sense, doesn't really make fun. But probably it works after some time, so Ledger is back again, and then basically we have the payment successful, but still it's not really a resilient way of doing things, and we tried to solve these problems, right? We did retries, and we did timeouts, and then we introduced circuit breakers. We did all this stuff, right? And then if you need to synchronize them, right? There's an important part here, because if you don't synchronize your timeouts with your retries, then you start to DDoS your own services and everything. Yeah, and just want to cry, right? At the end of the day, it's one of these days then. And this is what we tended to call kind of the first generation of microservices, right? This is how my personal microservices, I would say 7-8 years when we started this in first client project usually looked like, right? We had we didn't know better, right? We had this synchronously integrated microservices, and we didn't really get a lot of advantages in terms of resilience, right? And then, of course, we said, okay, Ledger is kind of an unreliable guy. Let's kind of abstract him away. Let's kind of make him not so unreliable anymore. At least let's decouple from him, or let's reduce the blast radius when it's not working. And that's where we started to introduce queues everywhere, right? So we didn't go to the ledger exactly. We just created a transaction on the queue. And this solved all our problems, right? Because then we basically place this transaction on the queue. A queue accepts it and says, yeah, cool, I have it. I will ping the ledger as long as you want me to ping him. But actually, you're done here because I will take care of it. And then basically, you can tell the user that you accept the payment. And that's a very important change here. I'm not sure if you spotted it, but we changed to, we accepted the payment, right? We didn't create it, we didn't perform it, but we accepted it. In terms of HTTP codes, we changed from 201 to 202, right? From created to accepted. So we tell the user, we do our best that we at some point in time will have it finished, but currently it's just, you know, somewhere in a queue. We cannot actually even tell you how long it will probably take, right? And we started to then, yeah, basically when the ledger once is back up again, he will proceed this transaction. And then, you know, if you isolate one bottleneck, that's the big rule of bottlenecks, then next bottleneck pops up, right? And then we started to put queues between, I don't know, the user and the account service, and ultimately between the web banking and the user service, right? And this was actually the time when AMQP or classical message queuing systems like RabbitMQ or ActiveMQ or yeah, all these other queuing solutions had their big time, right? And this was, of course, a big step already, because we moved, so to say, from synchronously integrated microservices into asynchronously integrated microservices. And yeah, it made our system quite a lot more resilient. But, I mean, I would be fully disappointed if I would sit here now and would see this architecture, right? Because obviously there's a big elephant in the room here, right? Yeah, unfortunately, you see microservice architectures often explained like this. You would probably find this example the same way on the internet if you go Google for, I don't know, microservice blog posts, 101s or so. But if you would talk to your product owner, and if you would have a good product owner, he would probably tell you a good user story, which you need to implement as a team, right? And he would tell you, you know, as a customer, I want my transactions to be booked by the ledger, right? And that sounds great because you adopt the ledger and the user story is done. The problem, no good product owner would ever tell you such a user story, right? Because no customer is interested somehow if your transaction is booked on a ledger or, I don't know, somewhere else on a MySQL database, right? Nobody cares, right? The user doesn't even care if there's a transaction, right? Doesn't really need to know this. And as a better solution, maybe the product owner would say, as a customer, I want my account service to update my balance. That makes already a little bit more sense, right? So, yeah, if you want to do a transaction, your balance should be in sync, kind of. But still, that's not something which users really care about. That's not the impact on the user. What a user usually wants, and what would be a good user story, I guess, I mean, I'm not an expert in user story writing, but what I would expect is that as a customer, I want to transfer money from someone to someone else, right? And that's a high sophisticated user story, right, in the banking industry. And the problem here, of course, now is that if the product owner comes to you and you're kind of, I don't know, responsible for this from a technical perspective, you need to go to the user service, need to say, hey, you know, we have this complex new user story of triggering a payment. I don't know why we need this, right? So we need to extend the endpoints on the user microservice. We then basically need to go to the account service and say, hey, you know, the user service has a new feature and you need to provide this functionality so that he can call you, and then you need to adopt it. And basically then you need to put an event or a command into a queue, and then the ledger team actually needs to pick up this queue, so it's just, right? You need to go to 3 teams to actually deliver some customer value. And that's also not something new, I tell you here, right? This is the so-called entity service anti-pattern we are all aware of and we all want to avoid. And we started this, right? Everybody talks about customer journeys. So let's create services along customer journeys. Let's move our systems more into vertical slices. And this idea, again, is age-old. A friend of mine sent me this paper, and it's really fantastic. You should read it. It's from Panos. So Panos did a lot of papers back in the days in software architecture. It's from 1972, and it's about the criteria of how to decompose systems. And basically what he says, he has different terms, but he says we should actually slice our systems or our programs based on user flows and not based on data objects. And that's exactly where we are again, right? So it just took us about 50 years, right, to re-understand this again, and that's where we are, right? So let's create services along customer journeys. So we did this. Again, we did this. We did a great job here. You know, you can solve every problem in software engineering with introducing an additional layer. So we named our services to domain services, and then we introduced something which we tend to call customer journey service or journey services, right? For example, payment would be such a journey service, and this payment service then actually just calls basically the domain services, right? And if the product owner would then come to you probably and would say, hey, you know what, I still need this important user story that we can finally trigger a transfer of money, and then you would probably need to go to 4 teams now, right? So it wouldn't really improve your situation a lot. Huh? And even worse, that's why I put this on the slides, because I think it's so important, right? In many situations, we started to move these customer journeys into the generous or very, very good pattern called backend for frontends, but we totally misused it, right? We started to put customer journeys into backend for frontends, and then basically we had a web backend for frontend, and we had a mobile backend for frontend, right? And then basically we had to have this payment flow logic twice, and then we duplicated it, and whenever you want to change the payment logic, you need to go to 5 BFFs and 5 domain services, and everything is really just not even a little bit better as it was before, right? So very important disclaimer here before we come back to the topic, because I see it so often misused, this backend for frontend pattern, and I was a big advocate of doing backend for frontends, but there should be no domain logic in backend for frontends, right? Backend for frontends are just aggregation layers for the UI living on a backend. But yeah, let's get back to our problem with customer journeys, right? So what's the problem here? Why do we just not move everything into payments? Why do we have those 4 services, right? Well, maybe if you have another customer journey service like balance, yeah, you want to show the user the current balance. Then this balance microservice would obviously also need to have account information, right? And ledger information. And that's the problem here, right? The hard part about distributed systems is it's not always how you slice the services, but the hard part is usually how you share the data between the services, and especially when it comes to customer journeys. And that's what I tend to call the customer journey entity data mismatch problem. Yeah, I made up this term a few months or years ago already, so you don't need to Google it. You will probably not find it, but I think it describes the problem very well, which we have here. Because if you think about it, it's given that each system basically has 2 things. It has entities. You cannot get rid of them. Even if you slice it along customer journeys, you will always have entities. You will always have end users, you will always have accounts, and you will also, for example, have transactions, right? But on the other hand, you have customer journeys, and this customer journeys usually provide value to the users, and you want to be as autonomous and independent in developing them. So if you, for example, have customer journeys, which are called, as mentioned already, payment, onboarding, or fraud detection, then those customer journeys need entities. And the payment, for example, needs a user, an account, and even a transaction. And the thing is, they are not one-to-one mappings. Customer journeys don't map to entities, because onboarding, for example, needs users and also needs accounts, right? Because it creates a user and then it creates an account. And fraud detection probably needs accounts and transactions. So we have this overlap of entities across customer journeys, and that's the entity customer journey mismatch problem. And if you think about this, it's all about these entities, right? So as I just mentioned, we have then actually here this fantastic error madness where everybody actually needs account data, and if the account service is not available, if it fails, whatever, then we have big troubles. So how can we solve this problem? Well, a simple solution would be, as I mentioned before, just get rid of those entity services, right? Just move all the data to payments or to onboarding or wherever you want to move them. But of course, this is of course fantastic if you think of service autonomy, because each service would be fully autonomous. But we have, of course, again here a big problem in terms of data duplication, right? So every service obviously has an account now. how do we synchronize this? And that's also maybe one of the key messages. If you take something from this talk about distributed systems in general, then I think it's very often unclarified, and it needs much more clarification who owns which data in such systems, right? So always, first of all, we need to understand who owns which data, and usually good indicators are those who create those entities or those who work mostly or update them mostly. So in our situation, we could, for example, say the onboarding service owns the user, right? And the payment service owns accounts and transactions. And then we could say, okay, if the payment service needs a user, then we go to the onboarding service. And then we have again a synchronous call, right? That's what we didn't want to have in the first place. And of course, we can again work with caching and so on and so forth. But if our onboarding service fails, our payment service fails, and then we have again resilience issues, right? And this, I mentioned, yeah, we can overcome most of these issues with some highly sophisticated caching solutions, and then we run into cache invalidation issues and all the things we actually know. So there must be a better solution. And now everything closes, yeah? Because I showed you this important sentence, right? When you remember from this simple code snippet, we project data from our counter variable into our doubled variable. That's what we did, right? And what we want to achieve on architecture level is actually that we want to project data from our onboarding service into our payment service. So for example, we have, as I mentioned, the user entities on our onboarding service. And what we want to achieve is that we have them projected into our payment service. So how do we do this? Well, if you think about this more in domain-driven design terms, then you would on the one hand side have the user aggregate, and on the other hand you would have the user read model. And whenever you change the user, you would send the user change commands to this onboarding service. It would actually update the user aggregate and would produce probably a user changed event. And this event then in many situations would basically update the user read model, and that's CQS in a nutshell, right? And what we then usually do, and now it's your time, Manuel, is we introduce streams, right? So we publish this user changed event to a stream, we transform it, and then basically we apply it to the user read model. So it's, again, very similar what we did on this simple JavaScript RxJS example on an architecture level. And one solution to do this, of course, is Kafka, but there are lots of other good solutions out there, right? There's Apache Pulsar if you need more, I would say, tenant-aware event streaming systemes. There's KubeMQ, which is fantastic if you need Kubernetes native implementation of such an event stream. Or you actually could even use Redis, which is really already very strong if you want to go with streaming. So it's not only Kafka, but we all know Kafka is, yeah, everybody starts to use it now, obviously, and there are reasons, but yeah, it's not always the right choice, of course, yeah. So let's come back to this example. So what would we do? If somebody creates a user, we would publish this event that the user was created to our stream, whatever stream it is, right? You know which stream it would be on my project, but doesn't really matter, right? So we would publish this event, you would consume it, and you would put it into this user read model of the payment service, right? And if you have, and basically that's what we have here, right? We have this, what we tend to call it, has different names. Some people call it read models. I usually call it projections. So we have this projected user data persisted somehow. It doesn't need to be a database. It can just be in memory. It can be in Redis. It doesn't really matter. It can be unmaterialized, different data sources for do this. But in the end, we have it there, right? We don't have it as a source of truth there, but we have it for simple reading. And when another user comes there, we basically do the same thing again, and we also move it to our projection. And we can do this then actually with all the entities we have here. We can do this with transactions, from payments to fraud detection, but it doesn't really matter. The important thing is now, if onboarding gets killed, right? Payment still works because we have our perfect user projection there, right? We have our users available there and can probably still operate at least some non-changing events on the payment side. So that's basically a very fundamental idea of this whole event-driven architectures, right? And we have this service autonomy, obviously now, right? We have them, so we can basically run those services very independently, and they're very resilient on their own, right? But now the question comes, if I explain this in workshops or so, then usually people always say, but there's eventual consistency, right? The first thing is eventual consistency is really hard, at least for me to define, because I think a lot about this, and I think we need to clarify a little bit what we need to talk here. Yeah? I don't go into detail now about eventual consistency. Could be so if you're in the workshop tomorrow, we'll talk a lot about this. But basically, I usually split up eventual consistency into three things. Yeah, on the one hand side, we have eventual divergence. So we probably have, as I mentioned, user changed events. So the user, I don't know, changed from age 21 to age 22. And then we probably have multiple services which consume those events, right? So the dashboard service consumes the user changed event and consumes the second user changed event and basically has a user in its projection with the age of 22. The profile service, for whatever reason, consumes it maybe in a different order, right? Uses the user changed event with age 22, the user changed event with age 21, and then ultimately has a user with the age of 21, right? And that's the problem, that we have the same events, but we come to a different result. And these problems can often be solved on a technical level already. So most of the streaming systems we have guarantee some ordering, at least on partition level, right? But if we don't have this, or if we cannot trust this for whatever reason, then we can simply work with timestamp and can window those things, or can check, okay, was there already a new event applied, and I just throw away the old one. So this seems to be a solved problem, I would say. Doesn't say that it's not complex. If you work in these systems, you always need to be aware of this, that ordering plays a role, and that it's important, but you can actually overcome those issues with, I would say modern tools and understanding about patterns, how to overcome this, right? And the other part of eventual consistency is eventual variance, right? And eventual variance, again, goes into this direction of having, for example, the ledger posting a transaction to the stream, and for whatever reason, this ledger cannot post it to the stream, cannot reach the stream, so the connection is broken probably, right? And then we usually try it again. So we do it again and probably it goes through, but we don't get the response, and then we try it again, and then ultimately it works, and then we have it 2 times there. And then if the dashboard starts to collect those transactions and sums them up, we have a balance of 20, but we should have a balance of 10, right? And this is basically the fact that we have the same events, but in a different quantity. And we can again solve these problems, right? We have patterns for deduplication. We have idempotency when it comes to events, so that they don't are getting applied multiple times. So again, we need to be aware of them when we build those systems, and we can solve them. But ultimately, they are not a roadblock anymore, right? But what we usually mean when we talk about eventual consistency is what I tend to call eventual latency, right? And latency you always have in asynchronous systems, right? That's the whole promise. Yeah? Nice word joke, right? So they promise you that they do it at some point in time, but they never give you the real hint when they do it. So in this situation, for example, if you have this user changed event, so everybody can create a projection of the user with the age 21, and then the user gets older, and then we project, and for whatever reason it works for the profile service, so the profile service updates its projection, but kind of the connectivity between the stream and the dashboard is broken, or is currently network outage, whatever. So we cannot update here, and the user comes, goes to the dashboard, sees, okay, my user is 21. Oh, I go to the profile, my user is 22. What a shitty software, right? And as I mentioned, I mean, this is hard to solve in 50 minutes, but in general, I think what's at least my simple solution to this, or what I usually ask the people, is that the interesting part about eventual latency is that it's usually just important in a single user context. And what I mean with this is, if I, for example, change my age from 21 to 22, for me it's important that it's then updated everywhere. Or if I remove, something and then it's existing again on some different screen, then that's for me a problem. But if I change my age to 22, and then somebody here still sees it on his screen as I'm age 21, I'm obviously not age 21 or neither 22, but then it's usually not such a big problem. So we usually have this problem on single user context, and that's why you usually also need to solve it on the client. And we have this perfect idea of optimistic UIs, where you'd probably then store locally in a cache that the user changed to 22, and we act as this you know, this command was already performed successfully, and if it didn't perform, we need to roll back. It's a little bit more complex then, but in general, we can move this problem, or we can solve this problem very often on client side, also on UX perspective, but we really need to be aware of this. We need to make everybody in the company aware that we now build a system which is based on asynchronous means, and this also means that we need to sync these problems on the UI, and then we can easily solve them. I see lots of people solving these problems very complex on the back end, but as it's actually a single user context problem, you can easily solve it usually on clients, and it's even a single user context, single channel problem, right? If I change my age on the smartphone, and if I go to the web application, it's usually okay for me if it's still outdated there, but at least, you know, on the same channel for the same user, I want to have this experience. Of course, heavily simplified, yeah? As I mentioned, all the three are heavily simplified. Now I just want to talk a little bit about eventual consistency, because it's often seen as a roadblocker, as a problem when we go into event or reactive systems. So these three are actually very simple to remember, right? Eventual divergent means that we have the same events but different results. Eventual variance means that we have the same events but in a different quantity, and eventual latency means that we have the same events but in a different realization. And we solve them usually by ordering guarantees. We solve them by at least once deliveries and deduplication mechanisms, and we solve them by optimistic UIs. Okay, so the short part, eventual consistency, often is used as a knockout argument, but isn't in most cases. So we usually can overcome those problems which we have with eventual consistency, right? So back to our problem. The cool thing was actually that with an event-based architecture, with a streaming architecture, or with reactive architecture, we can get rid of these resilience issues that if one data is not available, then the other services stop to work. And that's basically really a big thing. Because if you think about this, with the service autonomy, you can solve a lot of really important business challenges. And I come up with this age-old example all the time, because it was one of my first biggest microservice architecture projects where I worked in. And I'm not even sure if the numbers are fully correct. Maybe it's also 92 or 94, it doesn't really matter. But I worked once with a German bank, and what we basically did there is that we built a kind of a mobile banking application. So back in the days when in Austria, for example, George was really cool, right? Everybody loved it, and then all other banks wanted to do something similar. And the interesting part was here that there was a research going on. I guess most of the banks did a research back then, but this research was interesting because it basically said that 93% of the users, all they do is to check their current balance and the latest transactions, right? And 3% of the others initiate the new payments, and 4% do something else like locking a card or so, right? And this made me an advocate for I would say, agile software engineering also, because if you think about this, right, and if you go to an engineer and tell them, hey, build a new mobile web banking, then he would probably invest 5% of his time in showing the latest transactions and balances, and 80% of his time in tinkering around how we can lock a card, right? And so from a priority perspective, it's very interesting, but also actually from an architecture perspective, it's very interesting, because if you think about it, then 93% of the users are just happy if they can see the latest balance, the current balance and the latest transactions. So if you think about it, if a user goes there and triggers a transaction, then we update the transaction, we publish the event. We have read models, for example, on the overview customer journey, where the user sees the latest transaction, the current balance. We basically just update it, and basically we put it then in the read model. And yeah, we have this projection there. And we can basically just read from the web banking application, from our overview customer journey, the current balance and the latest transaction by just going to this read model. And the cool thing is that we could start to burn things now, right? Could burn up the onboarding service, we could burn up the payment service, we could actually burn everything up beside the overview service, but we can still deliver 90% of what our users actually expect from us, and can still perform this, so showing latest transactions and showing the current balance. And beside this whole impact on resilience, we can also easily horizontally scale this architecture, right? We can say, you know what, so many people are currently checking the overview, we just spin up a new service instance. We create a new projection, which is basically fully independent. And if we have a high load, our web banking can go to instance 1 or instance 2, and we basically can easily spin them up because we have this stream of latest transactions and current balance. So we can easily spin up these new instances, right? So these applications or these architecture seems to be easily horizontally scalable, and that's another advantage besides the resilience aspect, that we also have this elasticity when it comes to reactive architectures. So if one of them fails, it doesn't really matter because we just spin up another one, right? And another thing which is often underestimated, but I think very cool and a nice free giveaway, so to say, from reactive architectures, if you do, for example, this payment performance or this performing a payment, what I showed before, then we go to the payment service, trigger a transaction basically, publish it again to Kafka Stream or to a stream. This stream is consumed, is put in a projection, and basically then we can directly push this change also to the UI, and we can say, in real time, okay, Lisa sent you 20 euros and your current balance is on real time updated, so you don't need to hit refresh or stuff like this, right? And this is where we usually use GraphQL because it comes with first-class citizen support for these kind of subscriptions, where you can then really go into these end-to-end reactive systems, where you work best with just having mutations and having subscriptions, but you never need to, pull for state. You always get the latest state pushed into your application. And this is where this gets really powerful, because you have out-of-the-box real-time capabilities. But also, for example, for our favorite, right, working with legacy systems, yeah, having legacy systems, right, which are always tough. We all know this. I spent lots of my past or my project lifetime in actually monolith decomposition, and decomposing monoliths is already hard, but actually decomposing databases is even harder. And there, for example, we can work with this concept either. We can work with change data capture. We can, for example, publish user changes onto a stream, and then we have our own projections there. And if our legacy system doesn't work for whatever reason, we can still have a resilient system beside this legacy system, right? And we kind of have this decoupled integration, which usually is a good tool, not the only tool, but a very important tool, at least for us, when it comes to monolith decomposition. And you can, of course, also do this in another direction, and so on and so forth. And that's what I usually tend to call the third generation of microservices. Yeah, we are fully reactive, so we are high resilient. We support horizontal scaling, or we support real-time integration, and we have good integration actually with legacy systems. So seems to be like a match made in heaven. But there's even a cooler thing, right? So if we think, really, I'm nearly done, yeah? That's just really the last cool thing you hear from me today. If you think about dimensions of scaling, then you probably know about, the vertical scaling and the horizontal scaling. Everybody knows this, and we often, on an architecture level, strive for horizontal scaling. So you would like to create new instances instead of, boosting existing services, because especially in the cloud, it's very expensive. So it's much easier to, just spin up new pods. And that's why we often try for horizontal scaling when it comes to architectural patterns. But what we often don't see, and I guess vertical horizontal scaling is clear for everybody, but what we often don't see is that there's a third dimension, and the third dimension is what we usually tend to call sharding, right? So we can also shard our services based on, for example, user groups. So we can say, we not just only horizontally scale, but we also shard them, and we say, users, I don't know, based on a specific name are going to a specific service, or users based from a different country going to a specific service. And then we can even actually horizontally scale in those shards and even vertically scale in the shards, and then you are, I would say at the place you want to be when it comes to scaling, yeah. And basically, this is what we then usually do, right? We shard them and horizontally scale them, and this is when it really comes to, I would say stream-based architectures, where we have, for example, this user-triggered payment, and this user-triggered payment is based on the user sharded into different into different partitions, for example, in an existing stream, and then we have for each of those partitions service instances listening to, and we can say, okay, cool, I'm interested in this stuff now, and basically it lands in the shard 1, so the instance 1 needs to deal with this message, and so on and so forth, and so we can basically build our whole system based on these shards, and we basically then can shard our system very easily in multiple dimensions, and ultimately we can still utilize this projection topic which I just mentioned. For example, here when we do a transaction on the ledger and basically store it in a partition on our stream, then we still would probably need this information for the float check, which is a little bit earlier in the stage. And we have a big advantage here because we don't need to project the whole stream into our fraud detection service instance. We really just need to project the shard we're interested in. So we basically also do sharded protections, which usually make system then much easier to scale because we don't have these bloated projections. We really have on-point projections for, let's say, user groups, right? And then we are basically very independent even on these shards. So we have autonomy on the shards. And then, we usually did this then with Apache Flink back in the days. Now you can often use Kafka Streams to achieve a similar result. And then you post it somewhere in Elastic, which in itself again uses shards. And then you basically have your web frontend, and the web frontend then just goes to Elastic and sees the transactions, and you can never kill this system, yeah? If you build it like this, at least from my perspective, right? So you can put there thousands of transactions into the system because you can basically infinitely shard those transactions if you design your system good enough up front. And yeah, as I mentioned, there's massive scalability in those stream-based systems, right? And that's actually, I would say, the last evolution step of microservices to go fully stream-based. And we have massive throughput, we have extreme scalability, and we of course not always need this, so let's sum up, right? So many choices as usually, what should we do, yeah? And probably that's the most important part of this talk. Well, I didn't mention one important thing, and that's the monolith, right? And actually, everybody still, I think, who works in software engineering for quite a time is in favor of monolith first, yeah? Start with the monolith, stay with the monolith as long as you can, because afterwards it will not get simpler, right? So start with a monolith, maybe migrate it to a monolith, and you probably think of doing this synchronous microservices first. Forget it, don't do it. You basically just build a distributed monolith. So really, if you have scaling issues in terms of teams, start to modularize your monolith first. Go in this, no buzzword monolith. And if this at some point in time doesn't work anymore because you need independent deployments, all this stuff, then go into asynchronous microservices, right? So go into this idea of sharing data or basically integrating interactions asynchronously. And then you basically anyway run in this problem of shared data, which I mentioned before. And then you need to make the shift, yeah. Then you need to go from a pull-based architecture and a push-based architecture, and this is usually where we tend to talk about reactive architectures. And if this is not enough for you, which I would probably not believe you, but if it's still really still not enough for you, then you can go into streaming architectures where you really then actually have this additional layer of scalability when it comes to shards, and there you have massive throughput. And as always, all of them make sense, yeah? If you move from left to right, it usually makes sense, and you get more features. When you move from left to right, you get more availability, you get more resilience, you get more scalability, you get more throughput. But as often, or as actually always in software architecture, you pay these features, right? And you always pay them with complexity. That's always the currency, the price of I would say, feature-richer architecture, which we need to be aware of. So the hard part is actually finding the sweet spot here on those lines where you still have enough features from an architectural perspective, but have just the right amount of complexity. So that's it, basically. This was the rise of reactive microservices and the future of fully stream-based architectures. I hope this was useful. Thanks a lot.